Hello, welcome to another coding session. Last time we made our thread pool, and the next thing I wanted to get onto was like an easy way that we can distribute work across threads. Like if we have an array of data to work on, just an easy way that will basically use a thread pool in the background to distribute everything across threads. I had a bit of a, there seems to be a bit of a theme these days. Usually I have a bit of a play to see whether I can make it work. And quite often I come across some problems because there's some features our language needs and it doesn't have. And that was the case here. And I feel like there's enough missing that I should probably do a session of just adding these features so that we can really get stuck into our thread distribution, whatever you want to call it. I do have a name in mind. Let's wait till the next one for that. So one of the things, I think I'm going to comment out this guy and we're going to go back to our OpenGL code. Fingers crossed it still works. And it does not. Okay, so I wasn't intending on doing this this part, but let's get onto it. I know why it's doing this. It's saying that OpenGL error is not defined. And the reason it's saying that is because I kind of took out the bit of code which makes sure that all of the procedures are in our identifier list before we start type checking everything. So let's bring that back. So I think we need to split this out into another loop. So this top loop is just going to be about types. So this is where like we come into type checking basically. We're type checking the program and first, you know, we initialize our identifiers with some built-in things. Now we resolve types. Just make sure all of the type stuff is sorted. Because after parsing, the parser doesn't know what's a type and what's not. It's only from this list that we know what are types. So we convert everything into a type if it needs to be. And here, I want to get rid of this procedure stuff, which I think means we don't need this either. So we could probably just turn this into a single if. So if it's a type, so we've established an assignment of a type. So actually, okay, we're diving into stuff that I didn't really intend, but when we come into here, there's actually, like, this is the type checking of an assignment, and there's actually a lot of stuff which is kind of like saying, you know, if it's not a type, do this. We're switching on type here. If it's not a type, do all this stuff. So I think what I'm going to do is, like, basically this is the guts of it for types. Where the length of the children is 2, I think we've kind of established that as, yeah, we've established that here already. So if we're assigning to a type, let's try and go back here. So we've established that we're going to go into here. And not there. Once we're in here, we know that it's not going to be procedure stuff. So we can skip this if. So we come into here. And this is basically all like stuff that has nothing to do with types. Right? So basically, yeah, basically it's just this. This is all it is. So I'm going to take that out, put it up here. So we do need the LHS node. So, but I guess we don't really need it unless we come in here. Looks like we also need the RHS node, which would be child 1. So let's do that. So basically this is like when we make type aliases, this is making sure the type aliases are also in the identifier list. That's the idea behind this. I guess I could have put that also in resolve types because that's recursive, but I'm not going to bother. And I think that does actually have some implications that I don't really want. So now the thing is that we shouldn't come in here. We shouldn't come in here if right-hand side is a type. Or if left-hand side is a type. This is saying right-hand side is a type. And this is talking about where the left-hand side is a type, actually. But I think for now, we're just going to like cut all this stuff out. And like you shouldn't, I want it to be that this should not be to do with types. Because a lot of this stuff is saying like, if it's not a type, then do stuff. So let's just assume it's not to do with types. And if we get an error where it's come in here when it should be handling types, then we'll just fix it and make sure that it doesn't come in here. Okay, so this first loop is like doing a lot of type stuff. The second loop is where I want to do our procedure stuff. So this is saying like, okay, if we come across a procedure, and really I feel like it's static procedures. Oh, I always need to switch my keyboard. Yes, we have this notion of static. But I guess at this point we haven't made things static yet. So that's interesting. Okay, well, let's just do what I was thinking before and we'll just ignore that part for now. So basically I want to take the LHS node and yeah, so I'm basically adding the procedure to the identifiers. So that means that procedures can be out of order. That's the idea. That's the part we were missing at the moment. That's why this was not, we were calling this before it was defined, which shouldn't be an issue. And now because we're not actually type checking the procedures here, we need to type check them in here. So I'm going to take away this procedure part. So I think this basically becomes the same as the if above. So for type stuff, it ignores, otherwise we type check. Let's see, maybe that causes some issues. Looks like it does. Okay, interesting. So the issue is when it's actually run. So let's just comment out a whole bunch of code. Oh. Like that. And see if that has an issue. It does, even that has an issue. And all we're doing is those four. Because I think I have the test disabled. Yeah, I do. I mean, it could be the standard library that it's happening in, even. But standard library code should not be getting executed yet. So let's try we're just doing one function call. That's like the whole program. So if we go up here, what are all these assignments? Okay, so we do have an issue with the staticness, because I have a feeling, like, why are there a ton of assignments? I have a feeling that all of these are generating assembly when they should not. That's what I was worried about. Because we're putting them in, but we're not saying that they're static. Is that it? This is going to be a bit more of a pain in the ass than I thought, because at this point, or maybe I can just go like this, set the allocator to static here. So normally I was doing it in here under this condition. So maybe I should also add this here. It's not a struct member. So that is the same condition. And let's take this out because it's handled up here. So that when we grab stuff out of the identifiers, the type node is going to be static. There we go. Okay. Yeah, I was thinking about explaining the staticness, but if you've watched some other videos of mine, you will understand the staticness. Okay, now we have a bunch of little tiny triangles. So it's running properly. So we're at least at square one now. So let's actually implement a feature. And the first feature I wanted to implement was type conversion between different kinds of numbers, because this has been a bit annoying. So for example, this triangle count 1D, I'm going to make that an I64, and also the triangle count is an I64. And then I want to do something like this, which will convert. So that'll convert it to an F32. Right? Then we don't actually have to provide that type because it can infer it from this. Should be able to. Where's another instance where we see there's an underscore I32. So that needs to be I32. Let's cast that, cast it, like convert it. I think that's kind of it. So we don't actually need that much of it right now. But when we go to change stuff, we will. So right now we should get an issue like, we should get a better issue than that. The type checks the call. Identifier does not refer to a procedure. Yeah, so this is an issue. Also, it's going to be an issue. The identifier node has a type. Oh no, I think that's fine, but I think it's more like this, because it's not necessarily an identifier. Yeah, I think I want to change this to procedure, and I'll do the same here. We're talking about a call to be consistent, because it's not always an identifier really. No. Anyway, that's what I've gone with. So what was the issue? The type node is null. There is no type node. So what is the identifier node? Is the type F32. That's right. Okay. So what we need to do is have like an if statement here first, where we say, is it a type? Is the procedure node a type? And then we do some special checks there. And if they all pass, then we return true. So what do we want to check here? We need to check that the procedure has the right amount of parameters, which in this case would be 1. So this here, we don't have the type node. So instead, we just know that it's 1. That's the amount of parameters that there should be. Just expected 1. And what else do we type check? We type check the expression. For that node, so the param node can be this. And param node from type. So what type should it be? That's the question. So in this case, we're type checking the call. It could be any number, right? That gets passed in. So the param node, I guess we don't know what type it is until we do this type checking. Expected type node. So I guess we just say that we don't expect anything in particular. Right, let's just pass nil in here. So it's not going to confirm anything about it. It's just going to resolve what the type is. So now we should know the type of this node should be available. And we know the type that is being returned because that's this node here is that type. So I guess we need to make sure that they are both numbers. So we'll say return numerical. We'll do a linear search of numerical types. Yeah, so we'll say return numerical type. That's kind of the way I normally do it. I just take the non-plural numerical types, and that's so the return type is this type. And let's do the param. That'll be get type of param node dot value. So that should say if it's numerical value. We're just going to say dot value instead of, like, it can't be a reference, it can't be an array or anything like that. It needs to be just straight up the number. So then if that's not a numerical type, or that's not a numerical type, then we have issues, right? Then we need to throw an error. Failed to type check call. And then we can say, like, that type cannot be converted to that type. Let's try that. So it's, maybe I'll grab this out. Param type node cannot be converted to that guy. That'll do. So numerical can be converted to numerical, that's it. So we've made sure that it has one parameter and then that parameter can be as a numerical, and the return type is numerical. So now we need to apply the correct type to it. So let's create a type node. And the value of it is going to be, well, it's a call node, right? Which actually, this is another one where I would like to change this, because it's a special one, to have square brackets around it. Yeah, let's do that. So we create a call node, and then we need a parameters node, which should be the first child. So we'll append to the children this parameters node, and then the first parameter, parameters need to be identifiers. So this is just going to say value, something super generic. And we want this type, which will be a child again, and that will be, well, actually that type is the param type node, right? I do believe. And then we want to also add the return type node, which is procedure node. This is a bit funny because we're like adding a type node to a type. Does that make sense actually? Do we need to add this? Because then I'm thinking we'd go, you know, something like this. Oh yeah, so the procedure node is just a type. Okay. But this node here is a call node, and it's getting this type of information. At the moment, it doesn't have any. Okay, let's try that and see what happens. I think that's right. So we have a call, it has parameters. This is the first parameter, and then it has a return type. Cool. So I think that's all the correct information, and I think we've done all the checks we need to do. Maybe there's more, but that'll do for now. We can always add them as we need. Get type of node. Okay. Maybe about here we can say like if is type procedure node. We can generate a conversion call. Then a pointer. Is that right? Do we need this type node at all? Let's put this below because I don't know whether we actually need it. Give it some good old parameters. What have we got here? Child location. Child location for a call. Does it make sense for a call to have a child location? Yeah, it does. But I don't think it actually matters. Like it will get used when we're down here. Yeah, child location. But we don't need it for this stuff, I think, generating our conversion call. So let's just create a new procedure and try this out without these guys. Location. Yeah, I think we need a location. Generate a conversion call. So the main thing we want to do is we want to figure out like what kind, we've established here that they are numerical, but what kind of numerical are they? So the parameter type node is like, so we do need the type node, but I don't want to pass it in, I can't be bothered. So the parameter type node should be, we know the structure of this one. So I think we can just be a bit cheeky and say like, okay, so that's the parameters node. That's the first parameter. But actually that's the identifier, and this is the actual type node. And for the return, we're talking about this guy here. Okay. But we don't want to know if it's a numerical. We want to know more specifically if it's a float, atomic, or signed. Atomic, signed, integer types. So just go like this, so it's more specific. And then we'll do this. This time we'll do it for the return type. So what kind of integer is the return type? So now that we know our type information, we want to know how do we actually convert. So if the parameter, let's start easy, right? If the parameter is atomic integer or signed integer, because they're, I mean, from a conversion point of view, they're exactly the same. And the return is also one of those two. Then it really depends on the byte size. So if the byte size of the return is smaller, no, if it's greater, if the byte size of the return is greater than the byte size of a parameter, that's where you need to do something a bit special. What do I need to pass in the context or something? That's something I actually want to change at some point. Does that take care of it? Yeah. Okay, so how do we do a conversion of integers? So when we convert generate conversion call, I guess the other thing we also need to do is we need to generate the expression, right? Like we do here. Offset, I think we don't need to care about any of that. We're not actually doing a call, but we need to generate an expression. So the return location, I think it needs to be a register based on, well, obviously based on the return type. So what is it? Number, type, context. So we have register number based on the return type and the context. So we have a return location that we want to put it into. And we need our parameter node. So we do need, this is the parameter node, parameter type node is then the first, whoops. Well, I guess we can use, you know, we can go like that. Okay. So we evaluate the parameter and put its result in the location. So now that should be the input one, the input register. Now, if we're going from a bigger integer to a smaller integer, all we have to do is say, actually, we want this register, but we want a smaller version of it. Because the way it works is if you have register 10 or whatever, then in assembly, you can refer to that, you know, it's the same memory. Whether it's a 64-bit integer or an 8-bit integer, it's the same memory. It's just that if you refer to it with the 8-bit register name, it only takes the first 8 bits. So it truncates it effectively, and that's all you need to do if we're going down size. So all I have to do, so I guess this is actually the parameter location with the parameter node type. Like that. So now we just make a register with the same register number, but using the return type. And then it should be a smaller register because we've established that the return type is smaller or equal. If it's equal, that it's like a no-op as well. You know, there's nothing to do. It's kind of a pointless thing to put in the source code to convert to something that it already is. And actually, we could do an early out if that equals that, if they're the same, then also, you know, just return. Like there's nothing, we don't need to do anything. There's no conversion needed. Okay, if it's smaller, we just do that. Okay, so what do we do if it's bigger? Let's refer to Grok. What did Grok say? I believe it's just a move 0 extend. This is integers to floats or floats to integers or something like that. I did ask, yeah, between different sizes of ints. So there's 0 extension and there's signed extension. Move signed extend. That's what we need to do. So we can move from one register to another with signed extend, which means that it will grow to fill more of the register, but with an unsigned integer, all you have to do is like fill out the rest with zeros. But with a signed integer with 2's complement, it gets a little bit more complicated. I wonder if it's actually always this. That we would, yeah, I'm not sure. So here's some code where we write some assembly. Here we go. So we want to do a move signed extend with our 2 parameters. And I'll just give it a convert. And this is the print format line. Well, I guess something we can do is get a return location. I'm going to say return location, and I'm going to cut this out for now. And this is just like an early out. And let's see. I don't know if this makes sense or not, but this is what we're going to try for now. So now we should be able to do operand return. So we're going to basically going to copy from the param location to the return location, which is actually the same register. But this is the small version, this is the big version, and we're doing a signed extend. So it shouldn't actually involve two registers even, it's just extending that one register. So that should go from a smaller integer to a big one. Now what happens if we're going from an integer to a float? If we go into a float, what do we need to do? Well, is that what I first said? Into a float. So at first it was talking about using the FPU, which we're not using. We use SSE instructions with these registers. So this guy here is converting a 32-bit integer to a 64-bit double. Convert SI to SD. Load 32-bit. I'm wondering if there's like a 64-bit assigned integer. (64-bit) int. Oh, that's converting a float to an int. But we want to go. No, that's int to float. Int to float. If it comes from a register, it just uses the whatever size the register is, I guess. Here, it's going to take a 64-bit. So maybe we want to make sure that we're coming from a register. And I guess we do know we're coming from a register because we've established that this is going to be put in a register. So I guess that will take care of the sizing of the input. It will just know from the size of the register. That's my hope anyway. But this is the command. There is also, yeah, see, there's this one here. So this one has SS on the end and this one has SD. And that's the different precision. We might need this in multiple places, but let's just see. So byte size of the return type, go in here. So that's copying there to there. Yeah, so I think that's basically it. That register to that register. So this register will be a float SSC register, and this will either be an S or a D, depending on whether we want to go to a 32-bit or 64-bit float. So I guess that's signed integer. Convert signed integer to S. Oh, I think that's scalar. So it's just saying a single float because the SSC registers can hold more than one float. So if the param is a float, then we also have these different cases. So let's go float to integer. Well, let's see what between ints of different sizes. Okay, we've covered that one. Okay, there was an issue that I came across and fixed it. Float to integer. Yeah, so it's like convert TSD to SI, It's strange that one has 2 T's in it. Like, I don't know what all these letters actually stand for, but this is, so what was it? Convert TSD, I don't know, but we're going to cut out that D because that's the precision, I assume, 2-signed integer. So this, I think we can, because we have multiple places, maybe, but we don't always use it, so it might be a bit wasteful, but you know, this here we could do earlier. Here. Yeah. So here I wanted to get the precision. So I could get the param. I don't really know that it's very necessary to do this here, but let's do it out here. A little bit thinking like, you know, sometimes we'll calculate all this information and not even use it. But it's fine. Return byte size. So if the return is bigger than the parameter, then we do this conversion business. If we're going from here to here, then we do this precision business. Okay, that's back and forward between floats and ints, and then from float to float is the last question I think I asked. Between floats of different sizes. Yeah, so let's just convert SS to SD. So a very similar command. So this case we need both of the precisions. So actually we're talking like a param precision and a return precision. So what precision do we normally... Oh no, yeah, that is right. This will get substituted. So this here, we're going 2, so that's the return precision. And this is from, just lucky I double checked this actually, because this would have been wrong. Okay, float to float. So let's convert that to that. So it's like param to return precisions. And hopefully that should work. Should do all our conversions. There's like, I guess, 3 types of conversions involving floats, and then converting to a bigger integer, converting to a smaller integer is a no-op. So that's nice. So I guess, yeah, I guess if you want to optimize a little bit, you could always declare things as the biggest size and cast down when it comes to integers. Okay, I have a feeling this is gonna crash, you know, crash and burn. Let's see. Try and count I64 is not defined. That is correct. Hey, there we have our triangle. But didn't we have like a bunch of really tiny triangles? Why do we have all of a sudden a giant triangle? That's what I'd like to know. We had tiny triangles, then we did this conversion, and now we have giant triangles. So we need to make sure that our math here is using floats. So triangle size should be a float, right? float index. Interesting. -1. So if we find this in the code, this is where we call swap buffers. Then after that, we have a couple of assignments. Looks like this is just declaring something, and then this is doing some floating point stuff. So that's declaring. Yeah, I guess the next one is doing that one. This is our condition, our loop condition. Then we do a single assignment in here within the loop. I guess four, and then this is also a sign mask 4.2. So this guy here is probably, yeah, the equivalent of this. Yeah. So it's just declaring this guy. Just floating point, which makes sense. Scope start. So all the index stuff is using these regular registers, which makes sense, and then using floating point. Oh. Because R11 is an address. Yeah. So an address. Do we have actually any conversion in here? We do not. This should be a no-op. What I kind of wanted to see was down at the bottom of the loop. Here, like after the scope ends, then we have this assignment, which is, it's using floating point stuff. Because that'll be this assignment, right? So we're adding this, which is presumably our triangle size. Oh. My light died. There we go. So this is interesting. Why all of a sudden, so maybe if we go back up here, if we find link shaders, what we call link shaders. Here's link shaders, and then we have some assignments. Yeah, these two are I64 assignments, so yeah, 8-byte, just integer assignments. Here is an assignment where, okay, so we take some value way back where, and we convert it, sign integer to a 32-bit float. And that's our divisor. And we divide this constant by it and put it into this newly allocated space. So that apart from this, it makes sense. Why the hell? Plus 88? Converting it to a float, that's great. So this is what we're dividing by. This converted to a float. And this is RSP plus 88 when, like, it's defined right here. It should be plus 8 or plus 4 because we're just See, this is us declaring it right here. Why the hell has it gone plus 88? That's really strange. So before we get to conversion, so yeah, the first thing it does here is this. So before we get to conversion, we're figuring out, we're doing a copy to figure out, well, why are we doing a copy? Where is that? Well, the copy would be this, right? The generation of that expression. So if I go here and we step in and we're generating expressions, we go generate expression 1 and we're generating a primary. And it's not static, it's not a struct member. So we grab the variable position, which is 88. Why? What is the node value? The node value is value. That's a problem. Because I got it from the type. This is the wrong param node. It shouldn't be from the type. It should be from here. So when I do a call, this is a node. We've verified that it has 2 children, right? The first one is the procedure node and the second is the parameter node. So the parameter node is actually so let's go back to this and I'm going to put in here node.children1. That's the parameter node that we want. That's the node we want. Hey, now we have lots of little triangles. Okay, that was the issue. Cool. Okay. So that took a bit longer than expected. But we have conversion. We've only tested a couple of conversions. We've only tested actually downcasting integers, which should be a no-op. And we've tested converting an integer to a float. We haven't tested the other ones. But we don't have much time. And I really am going to get to doing like a proper test suite, and then hopefully we'll find out that these work or don't. But I kind of wanted to get onto another feature, but we're nearly at an hour. I think there's not going to be enough time for that one. But I do think there's a quick one we can do. This actually reminds me. So this is where we try to parse an assignment or a right-hand side expression. So we try both, and then we try to figure out like, hey, which one was better? Which one should we take? And at the moment, if one of these succeeded, we take it. And the problem with that is that it might start with something which is a valid right-hand side expression, like an identifier or something. But then after the identifier, that's it. And so this just picks up, this just parses like one token successfully. But this might parse like a whole big thing, get really far into it, and then find an issue and fail. But in that case, we don't want to just take this. Obviously, this is what it should be. So we should take that. And the reason that it even matters, like, is because if we take this one, then the tokens after it are not going to be a valid thing. It's just going to throw an error and be like, hey, why are you giving me this token like equals or whatever? This is not the start of a statement. It just gives us this annoying, not very handy error. Whereas if we take this one, then we get the actual error from inside the assignment that was causing the problem. You might have noticed in previous videos, I was kind of like, why am I getting this really shitty error message? And I kind of tracked it down to here. So essentially this gets simplified. It basically becomes this. So I'm just going to cut out all this stuff. So if parsing a right-hand side expression was as successful or more successful, i.e. it parsed more tokens than the assignment, then we take it. Which means that we need to return whether that particular thing was okay. Like that. Yeah, like that. So that should give us some better error messages. We don't have any error messages right now, but fingers crossed it does. And another thing that I wanted to do in here is we should be able to say like blah I64.3 and then blah blah is, can I just do this? I don't think so. But we could say blah blah is well, there's somewhere where I declare vec3, isn't there? Oh, no, I don't. No, I don't. Okay, that's cool. Okay, so I kind of had this vec3 in mind. So if we have a vec3, which is an array of 3 floats, and then we say vec3 array, which is an array of 3 vec3s, then I should be able to say, I should be able to go exit, well, I should be able to go vec3 array boom boom equals 1, or let's say like 7, or 42. 42 is a nice one. So if I go like 1, 2 or whatever, and then we should be able to exit with, we can convert now that same value, then we should get an exit code of 42, right? So I just want to confirm that that kind of thing works, that we can do 2D arrays effectively, indexing of 2D arrays. Pretty sure right now it's going to fail because you can't do that. Not a very handy error message. So what we need to do in our primary, because the way we've done things like the hat at the start of the primary is it recurses, you know, it recurses into parse primary. But for things that appear after, I think we need a loop. So these are the things that appear after. And we need to allow them to keep happening. So the way I'm going to do that is I'm just going to say like, well, we need to have a variable like found suffix. Let me just default that to true, and for sound suffix, then we do this. And I'm going to add a default case, which is found suffix equals false. So if we like, oh, I think I did put that in the wrong place. So if we go through this switch and we don't find something, yeah, that should be there. Then we say we didn't find something, and then we quit out of the loop. But that's because this is a loop now, it means that we could have multiple hats after, we could have, this is the important part, multiple opening square brackets. And of course we can get errors. Because when we try to auto dereference, we get problems. Because now we're trying to auto dereference something. Which is something we've never tried to auto dereference before. So we have an index node whose child is also an index node. That's probably the problem. So should we be auto dereferencing in that case? So what was the actual error? We tried to get the node type of the node and it didn't have one. Didn't it? It has 3 children, which makes me think that it kind of does. An index node. First child would be the thing that it's indexing. Second child would be the expression, like the index expression. And the third node, I guess, I would think would be the type. Yeah, see, this one only has 2 children. This one has 3 children. And that's the one that we're passing in here, the child. Another thing that I had thought of while we are here, this I'm not convinced is going to actually get us the identifier. Once we auto dereference, I kind of want to make it so that we can only actually index yeah, so if it's not an array and it's not a slice, then that's not a valid thing to index. It would take something like that. Cannot index. Like so. Then we don't need to do this check because we know that it's always going to be one of those 2. And then here we can actually say, like, if it is an array, we're going to do this, which means we don't need this. Like so. So we simplified things a bit, because before I had it so that you could index just a scalar, but the only thing you could index it with was 0, which kind of doesn't really make much sense. Not that helpful. Cannot index type boundless I8. Ah. For boundless, it actually does make sense. This is the boundless. I mean, now that we have slices, do we need boundless? That's the question. We need to be able to convert this sort of thing into a slice, and then it would be fine. We can't do that yet. So let's earmark this. We'll do this in the future. This is not a now thing. So now we have to go back to the error that I was avoiding. Not really knowing why this is an empty type. Why is it an empty? Why is there no type? Auto dereference. So the child node has been type checked. And I think that's why the child node has 3 children. Let me come in here and say like, and maybe I'll just say, get the 3rd child and see what happens. There should always be at least a 3rd child here, I hope. I guess not. In this case, there's only 1 child. So, something like that. We know there's more than 1. Oh, that's the 3rd one, actually. Okay. So the 3rd one apparently is an identifier, vec3. Ah. Because vec3 has only just been declared here. Oh, because it should be like this. It should be a type alias. That's the problem. How is that valid? No, I guess it was. No, I feel like it shouldn't. Like that wasn't a type. Now it's a type because I'm saying it's an alias. This was declaring an array of 3 floats. And this here was invalid. That should not have passed. Or it should not have type checked successfully. Okay, so let's try that. Now vec3 is actually a type. Okay. That didn't really seem to work. Ah, process finished with Xcode 42. It did work. Okay, that felt quite dodgy. I feel like there are so many issues in this language. It's kind of just ridiculous. Like the fact that I could just do that, and it's just like, okay, you know, this here, I guess this is okay. Yeah, there's a lot of holes in the language. That one is a bit of a tricky one. But yeah, hopefully soon we can actually like get a bunch more tests. Actually test a lot of these things. But I think that's enough for now. we managed to get basically 2D arrays working, or 2D indexing, I guess you could say. Or actually, it should be like infinite D. You should be able to like do that depending on how many Ds you have in your structure. And we got conversions working, and everything is tested in such a half-assed way. It's terrible, I know, but we will get to it, which is what I say about everything. All right, I think that's enough. Thanks for stopping by. Have a good one. Ciao for now.